All right, welcome everyone. I need to change some settings here, and we will be ready to start. Okay, I'm here, I'm back. And we are ready to go. I can see you have found the live chat window. That's excellent. Today, we are doing a small dry run of a clinic presentation that I'm going to give at the JMRI Pacific Coast Regional Summit in Bakersfield next week. And if all goes well and the presentation goes well and I'm actually able to fit the necessary material into the amount of time available, then we will run this clinic probably regularly on regional and national conventions. So let's get started. Here's what we're going to cover quickly today. At the beginning, I'm going to show you and familiarize you a little bit with the layout section that we're going to build during the clinic today. I'm going to show you the boards and all the electronic components that we'll be using in order to build this layout. Then we'll get into the middle. We'll start with cabling, wiring up the LCC bus. And we'll start JMRI, and you will be able to follow me on the screen with my JMRI windows. I'm going to show you initial configuration of the LCC components, and then we'll get into setting up the actual layout and the actual layout's control logic. We'll do initially just a simple sensor configuration, making the sensor show up in JMRI, show up on the panel display. Then we're going to move on to more simple accessory functions like throwing turnouts and displaying the turnout indication on the panel. And then in the last section, which might take about half the time, we are going to the really interesting and advanced possibilities of LCC, and that is going to be the signaling part. So we're going to set up ABS type signaling. There are a bunch of signal heads on the layout. And hopefully you will see all of those signal heads to operate properly according to the sensor indications that we are receiving from the block detector. This is a quick view of the layout that I'm building today with you. And let's get started. So this is kind of a minimal layout that I have found to be really interesting in terms of LCC and accessory control. We have a turnout. The turnout can be thrown with two separate fascia buttons. We have a dispatcher control panel that can be run on the computer, and the dispatcher control panel decides so then the local panel buttons can be locked out from throwing the turnout. I have 6 block detection sections here, And you can think of these as being long stretches of main line. Each of these sections is protected by signals. And the signals will obviously show the necessary indication according to the occupancy situation ahead and behind of the particular section. Let me get a quick check. Are you guys able to see the presentation correctly? Are you guys able to hear me correctly? Is the technical setup working for you? Please reply on the chat window in YouTube. Once we are when we are done with the signaling, there is also a railroad crossing. There's also a railroad crossing that I put up on the panel that can show us how we can configure. That can show us how we can configure a very simple occupancy-based railroad crossing setup. And there are a couple of different ways on how we can do it. So we'll see advanced features such as blinking, as well as occupancy-based signaling. So let's see what kind of boards we are using today for our Build Your Layout clinic. These are components from railroad circuits. These are all available for sale. Railroad Circuits is selling basically a starter kit for LCC. And this starter kit contains the LCC PowerPoint, which, as you can see, has the power supply, and it contains the bus terminators. We'll talk about the importance of the bus terminators later. They are selling a computer interface. This is also part of the starter kit. You can plug it into your USB port, and JMRI is prepared for talking to the LCC bus via this USB adapter. And they have a highly configurable and very flexible input-output board that can drive all of the existing I/O boards from the railroad circuits line. So you can connect input buttons, you can connect LEDs, you can connect block detectors based on the coil-based inductive detections. You can connect switch machines, all types of switch machines, etc. So basically, all the needs for your layout are actually covered by these I/O boards, and you would be using the same smart node, the same board to connect to the LCC bus, independently of what kind of what the particular railroading interface that you need. However, unfortunately, my supply of railroad circuits devices are stuck in transit. So today I'm actually going to use a couple of other boards from different manufacturers. The big benefit of this is that you will see more diversity in how LCC layouts are set up and configured. And I can also showcase how the standardization actually allows cross-manufacturer interoperation, because it's not very difficult to have hardware from one particular manufacturer interoperate with themselves. They usually test it, but here we're going to be using actually 3 different manufacturers' board. The second, this is going to be doing the block detection for us today. Next week, maybe I'll have the railroad circuits version of block detector. This is a 6-channel block occupancy detector. It has the plugs for the LCC bus. So it is obviously sending back the occupancy feedback via the LCC bus. And it has a number of extra features that we're not going to be using today. It's just for your information. I actually designed this board myself. We are going to use another I/O board from a third manufacturer. The manufacturer is called Railstars. This is a product that they put on the market around 2012, I think. It is an 8 input and 8 output I/O board. The inputs are active or basically just buttons, although we're not going to be using those inputs today. And the outputs, 8 of them are high power. They have driving transistors on them. And there are up to 32 additional outputs for direct LED drive. These are sockets which are plug compatible with the railroad circuits output boards. So you can use the railroad circuits I/O boards to interface to your layout, and the Railstars I/O boards to plug it into the LCC bus. So basically, you can use the Railstars board instead of that smart node, and you would be using the same ribbon cable to connect to the output board. The Railstars I/O board has a lot of different power options. It can be bus powered, or it can be externally powered, or it can even power the bus itself. This was a welcome flexibility at the time when this was the only board available. There was a question about the blocks. So BT is actually a block. So yes, there are 7 blocks. Unfortunately, I only have 6 block detectors. So we're not going to be using the turnout as a separate OS section today. I'm just going to lump it together with B2. So today, B2 and BT will be detected as a single entity. The JMRI required is, for all the features that I'm going to show today, it's going to be 4.7.3, which is probably going to be released tomorrow. But the core feature set is actually present in JMRI 4.6. Okay, so let's move on and let's start building our actual bus. The first most important question is always cabling. So LCC, as it is specified today, is using CAN bus as a transport. This means we can use standard commercially available cabling for it. We are using actual Ethernet cables. You can buy them very cheap on Amazon. It's actually so cheap to buy them prefabricated that it's not worth to try to crimp it yourself, because the possibility of errors or mistakes at crimping is just, it's too high a risk. It's not worth. The bus is very robust and noise sensitive, noise immune, sorry, and it can be pretty long. You can go up to 1,000 feet or 300 meters of cable length without having to do anything particularly special. There is an interesting requirement, however. There is a minimum cable length requirement. The minimum cable length is 1 foot. That's 30 centimeters. I'm going to show you quickly. So this is roughly the shortest cable that you should be using. There is an interesting story behind this. There is an electrical requirement about how close to each other different buses, different hardware can be on the bus, and it has something to do with signal reflection and attenuation. There are like long technical notes about why that is, but fundamentally, all you need to know is not to buy cables that are shorter than 1 feet. The cabling of the bus is linear. So every board that you have, that you buy on the, oh, there was another question. Does a crossover cable work? No, a crossover cable does not work. It has to be a straight Ethernet cable. Yes, all the wires that you use have to be straight. So when you're cabling up, every single board that you have will have 2 sockets. And you need to plug in 1 wire into each of the socket, and then create a linear bus using this. So you're basically daisy chaining the individual components. And when you have wired up the components linearly, you will always have 2 sockets that are free. And those 2 sockets you have to fill with so-called terminators. This is also required for the electrical stability of the bus. So make sure that you don't forget the terminators. Make sure that all the plugs are fitted with something. So the bus has to be linear. So don't try to create a Y or a Y-shaped cable or branches. By default, this is not going to be easy anyway, because you have only two sockets on each board. But generally, there is a restriction of having extremely short length of taps, like on the order of like up to a couple of meters in total for the entire bus. So don't use Ys or branches. You have to use specific boards designed for branching the LCC bus, if in case a linear topology doesn't work for you. So at both ends of the bus, you have to plug in the terminators. And let's take a look at how this works here. Here there is the LCC power point. That's where the bus starts. That's where one end is. You see the terminator circled. And then there are these 1-foot cables going from one socket to the next, always from board to board. And here the buffer USB has the other end of the wire and the other terminator accordingly. The next thing that is important for us to know is how power is distributed. LCC boards are required to be labeled according to their power needs. Normally, for a small amount of current requirement, it is possible to have power coming from the LCC bus itself. This is labeled clearly on the boards, whether a particular board is taking in power from the bus. For example, here the Tower LCC takes 20 milliamps of current, plus whatever it is supplying to its I/O boards. The Railstars board has multiple different power configurations, so it can take up to 300 milliamps of power, or it can actually supply power to the bus. You as the deployment, when you're basically wiring your layout, you have to decide whether whether you supply power to the Railstars board separately or from the LCC cabling. And here there is a picture of a command station, which is actually in my bus right here. This command station is able to supply 500 milliamps of power to the bus. So that's going to be quite convenient for us, because the 500 milliamps just is perfectly enough for supplying the Tower LCC and the Railstars board. There is one more important requirement, which is that the power supply has to be reasonably close to where you are actually consuming the power. So in my case, it's not that big of a deal, because, well, my layout is just a couple of square feet, so all my cabling is pretty short. But generally, you cannot have an arbitrarily long cable and still supply power through that. In fact, it's going to cause you a lot of headaches, because not having sufficient amount of power will typically give you hard to diagnose or detect problems, where some boards will not work as you'd expect, and they will operate in different ways. The general rule is that the power source has to be at most 6 foot or 2 meters away of the power consumer. And in my particular case, in this layout, the power source is in the middle. You see the blinking LED. And well, on one direction, there is only 1 feet of cabling. The other direction, there is like maybe 4 or 5 feet of cabling. So this is perfectly fine. So let's take a look at my particular layout here. So this is the Railstars board. I've already plugged in the panel. The Railstars board has a plug for external power supply. This is not necessarily true for all other boards. And then the Railstars board also has an option for internal termination. You will probably not see this in future commercial products. So because I've set the terminator here on the Railstars board, I'm not going to have to use a terminator in the plug. And then the bus starts from here. This is the command station that we're going to be using. We're not going to interact with the command station too much. The only important part for today's clinic is that it's actually outputting a DCC signal that the block detector will actually be able to interpret. The command station is actually powered from a power supply, and it is supplying current to the bus, as you have seen on the previous slide. Then my bus goes on. This is a tower LCC module. We're going to be using it to process some of the input buttons, as well as drive the coil drivers for the snap switch here. And this is the smartest board of the entire bus, which means we're also going to be using it for all of our signaling needs. The bus goes on here. That is the USB connection. And finally, at the other end of the bus, I have the block detector board, which I showed a picture of. This board I have made myself. And then the end of the block detector, the other side of the block detector, is a terminator. I have mostly wired up all the connections here. It is not super exciting to wire up the actual inputs and outputs. So in order to save time and for you not to have to watch me fighting with screw terminals and various plugs, everything is just plugged in here. The panel that you see in the back, that has no smart electronics at all. Basically, everything in the panel is just the LEDs, and the LEDs are wired up with power supplies. And I have basically broken out the individual LEDs into these ribbon cables. Apparently, I also ran out of ribbon cables, so I had used some other wiring as well. The back side of the panel is, as I said, it's not super exciting. It's basically just wires, resistors, and basically glue. So it would look basically the same way, independent of what kind of technology you are using in order to operate your layout. The LEDs here are wired in multiple different ways. Some of them are wired common anode, others are wired common cathode, so that you can see how it is configured differently. And you will have the ability to see the various configurations. Excellent. If you guys have any questions about the wiring or cabling, let me know. Otherwise, we're going to move on. So Okay, no cables. We're going to start the initial setup. So I'm going to connect with JMRI and add a new system connection. And we're going to see what we can see on the OpenLCB bus there. So I have to go here. I'm going to start Panel Pro. Hopefully it's going to come up. I'm going to create a completely new profile for you so that you see I'm not cheating anything by preloading configuration, etc. So we pop into the preferences window, hopefully. The system manufacturer is going to be set to OpenLCB. Yeah. And the system connection will be LCC buffer USB. Oh, I apologize. Okay, let me start this again. So I'm going to start Panel Pro. I am creating a new configuration profile called Clinic Run 1. We pull up the preferences window. And I'm adding a system manufacturer for OpenLCB. And I'm using the LCC buffer USB as a connection. And the serial port is the only one that it offers. So that's perfect. I'm going to save, and JMRI will want to quit for this to take effect. So I'm going to let them do that. I'm going to use the same for now. So there were questions in the chat asking if they have multiple power consumers that are more than 6 foot apart, how is the power supply accomplished? And the answer was that another power supply needs to be added, which is closer to the consumer than 6 feet. And that is the correct answer. Thank you very much. So the next step is to go and do the configure nodes. This is where you'll spend most of your time when you have an LCC bus. There is a question on whether this OpenLCB link here will be changed to LCC in the future. This is not really my decision to make. We can discuss this at, let's say, an OpenLCB users group meeting at a convention. There is some amount of political background to this, so I will not try to go into a lot of details about that question. So the OpenLCB bus has the ability to figure out who is connected. And when you call up this network tree, you will actually see all the boards that are connected to the network. So the top one here is the JMRI Panel Pro that I'm running right now. I have an RR Circuits Tower LCC, and then I have the I/O board, the Realcomm block detector that I have designed myself. And down here, there is the RailStars I/O board. The first thing that I'm going to do is to give them some sort of like easier to understand and recognize names than what is presented here. So I'm going to open the configuration dialog. And I'm going to set the usernames for each of the boards. So this is the tower LCC. I'm just going to call it West Bakersfield Junction Tower. This will do all the logic. And I have almost succeeded in typing this. Everything that you change will show up as orange. And you have to click the write button either on the right-hand side or the save changed button on the bottom in order to write your modifications into the actual board. If you do something that you didn't want to do, and you do not want to save your changes, you can use the refresh button in order to read the value from the board, and that will undo all your changes. So this is good for the tower LCC. I'm going to give a name to my detector board. It's entirely up to you how you name your particular hardware. You can use a username and the user description. I usually put some sort of functional description for the username and the location of the board in the layout into the description. And let's do this for the RailStars board as well. This is the panel node for West Bakersfield Junction. I'm going to see if I changed. JMRI will read the username and the user description for every node at the time when it reboots. So now that I have changed the usernames and the user descriptions, they are written to the board itself. And at the time of the next reboot of the board, JMRI will read it out again. So I'm going to go and reboot, let's say, the RailStars board here. It actually has a reset button on it, so I'm just going to go and press that button. And you guys can follow what happens on JMRI. So you see that JMRI has seen that this node has come up, and it immediately read out the particular description. So the names have shown up here. And after that, basically, the numbers are not necessarily meaningful to you. You only care about the particular description. I'm going to restart also the tower LCC. Let's just plug in and plug out. We have now the tower's name as well. And I will restart my detector board too. So now we have all the three boards. We have set the name, and we have rebooted the layout. So now JMRI has the username actually associated to each of the board. There was a question whether whether the changes are made in JMRI or saved to nodes themselves, the answer is that they are saved to the nodes themselves. So each of the nodes are actually carrying non-volatile memory where you can make the configuration changes to. And this basically allows you to carry your boards. For example, if they are mounted into a modular layout, you can carry your modular section to someplace else. And even without your JMRI, it will work and operate exactly the same way as you basically left at the last time that you configured. So we have done some initial configuration. So let's go and do some railroading. Events. This is the most important concept, basically, for the entire remaining of the presentation today. We are going to be working with events. When you have an I/O node on your layout, then the inputs that those I/O nodes have, they report when something has changed. So for example, the block detector board would say, block B1 is now occupied. Or at another time, it would say, block B1 is now empty. Similarly, when you have, let's say, an I/O board and it has outputs, those can be sent commands through the bus. For example, you can say, set the B1 indicator output to lit. Or you can say, set the B1 indicator output to dark. The really powerful concept in LCC is that these two are no different. These two are using the same concept. So fundamentally, you can configure the output to just listen to the reports that the detector has sent, and then the panel will immediately start to work. So the detector board tells what's happened on the bus, and then the panel driver will listen to that and update the panel indication directly. So even if there is no computer present, the layout as it is configured will just work because on this peer-to-peer bus, the different boards are directly talking to each other. So let's take a look at how this works in practice. I'm going to go back to JMRI, and I'm going to set up some of the panels with the detectors. So I'm going to open the configuration for the detector board. Let's put it somewhere aside. I'm actually going to make this slider. So I have the detector board, and I'm going to have the panel as well. This doesn't look very good. This definitely does not look very good. What is going on? I've seen this before. Let's restart JMRI. I'm going to configure nodes. And I'm going to open the detector board. And I'm going to open the tunnel. This is not working very well now. All right. We are better now. So the goal that I have now is to make on the panels, on the panel that is shown behind the layout, I want to make the blue indicator lights actually show the occupancy values that is coming from the detector board on the bottom middle. So here I have the configuration for the detector board. You can see we've seen the username segment previously. I will not care about the internal data and the LEDs and the buttons, neither the tuning params. It has 6 channels. And for those 6 channels, each of the channel has a name that you can configure. It is highly advisable to configure the names according to what your definition is. So in my case, I have wired them up directly so that channel 1 goes to block 1, channel 2 goes to block 2, channel 3 goes to block 3, block 4, block 5, and block 6. It makes no difference to the operation of the node, whether you give names to the particular channels, but it is extremely helpful for you as a person editing the configuration when you can see what the particular lines and members are doing. So in this particular case, let's say block 1 has 2 events, the occupied on and the occupied off event. And I am trying to make the sensor for the output button, the output for the output light for B1 to follow the same indication that the detector block B1 is sending. So I have, and I've actually sent you the mapping of the outputs to the particular numbers, and I know the names of those. So output 1 is BT, output 2 is B1 indicator, output 3 is B2, then T1 indicator closed, T1 is thrown. These are basically the wires that I have put into the screw terminal in this particular order to the board, to the RealStars board. So this is output 1 to 5, and I've just used my notes in order to figure out what actually I had wired in here. So far I have not configured anything here. I just basically made the situation a little bit more easier to oversee from my perspective. Now I'm going to show how to tie together the two particular event information. So basically, I want to make sure that whenever the block 1 occupancy detector says it's occupied, I want to make the B1 output activate, and when the occupancy detector goes unoccupied, I want to make the B1 output inactivated. So basically, the occupancy detector is directly driving the output in the sense that when it is on, occupied, the output is on. When it's unoccupied, the output will be off. So if I save these changes, then hopefully on the output, it will show up. And indeed, if I take off the locomotive, the block goes unoccupied. If I put the locomotive on, the block goes occupied. So you can see it clearly there that the occupancy of the particular location is showing whether there is a train there. Because of my demonstration layout, everything is compressed heavily. So while this may be a single block of main line, for me, it's basically the shortest possible length to which my locomotive actually still fits. So I have wired up B1 to be showing the same indication as the occupancy detector. So let's just do the same thing for the rest of the occupancy outputs. So I'm going to take B2 and wire it up with the output of B2. and the unoccupied goes to here. And then I save this. Now B3, 4, 5, and 6 is actually lined out to a different output block, because for those I actually had space in the ribbon cable. So B3, 4, 5, and 6 are on the ribbon cable. There is a trick here that I need to apply, because 3, 4, 5, and 6, the LEDs are wired up to be active low, but the plug that they are connected to is actually active high. You can see this from the fact that they are actually lit, even though no commands have actually arrived yet for them. So I go back, I have configured the names of B3, 4, 5, and 6 to the appropriate output numbers, and I'm going to connect them to the detectors. And because it is an inverted output drive, I'm going to swap the behavior by switching the two event IDs. So I'm going to take the occupied event ID and put it to the inactivation event. I take the unoccupied event ID, I put it to the activation event. And then I save changed. And ideally, if I go back to the layout, and I take the train, and I go to B3, and then I exit B3, now it has gone off. I enter B3, it has gone on again. Now I'm in B2. Excellent, this worked fine. So let's do it for the same for the remaining as well. So B4 there, B4 here, activation goes across, inactivation goes across. B5, activation goes across, inactivation goes across. B6, activation goes across, inactivation goes across. Now, there are a couple of interesting things that you can note here. Everything that I have changed and I haven't saved is in orange. This also works for tabs. If in this particular tab there is anything that has not been saved yet, the tab itself will show up as orange. The next important thing is, you've seen the copy and paste buttons. I've used that quite extensively in order to connect the events together. And then the third important thing to show for you is that when a particular event is configured, it shows you what other uses for the same event exist. So for example, in this case, I am pasting this number, but you don't know what the number means. However, you know that's the same number is used for the detector board on the channel called B6 for the unoccupied sense. And indeed, this is the B6 indicator. So that's pretty much what I expect, pretty much what I want. So I can go save changed. I apologize, I was talking while showing you the layout. So I showed you that if something is modified in a particular tab, then the tab is showing as orange colored. And what I showed you is that when a particular event is set, then JMRI will show other uses for the same event ID. So even though this particular number doesn't mean anything to you, you can actually see that that this is tied to the detector board occupancy detector unoccupied sense. And this is tied to the same channel's occupied sense. So they are basically matched up. And when there is no change anymore in a particular block, then it is showing up as a standard background color. Okay, let me see, there are questions. There is a question asking the detector board and the panel node are two pieces of hardware. The answer is yes. The detector board is here. It's this one. It is getting a high gauge wire from the command station. That's what's actually feeding it power. And then I have one wire going into each detection section. The detection sections are single gapped here, so I'm only feeding one of the wires through the detector board. So this is the detector board, and then the panel is driven by the Railstars I/O board. You can see that I have the flat cables coming from the back of the panel connected to the I/O board, as well as the few wires that were left over and didn't fit into the flat cable. They are coming here and finishing on the screw terminals there. So that was one of the questions. The other question is, I assume you could do the occupancy in a panel without the LEDs in a similar manner. I'm not entirely sure what that means. So all the events go to the network. Yeah, that's correct. It is possible to set up a board to sort of like respond to its own events. That's absolutely true. So basically, every single board has to listen to its own generated events as well, and that is part of the software of the boards inside. So there is always local loopback, and Node can always consume the same event that it produces. In this particular case, we will actually see that when we are configuring the tower LCC, because the tower LCC will be driving the turnout, and it will also have the input push buttons for the turnout control. But that's going to be a little bit later. So I have set up all the 6 block occupancy detectors. So I can drive around the train and I will see the detection output. I'll have to flip the turnout manually for the moment, because we haven't configured the turnout drivers yet. So now we can see that the indication on the panel is always following the locomotive. So the next thing we can do is, this indication is not, we have wired up the panel and the detector board. Let's do the same thing with JMRI. So let's teach JMRI to see the same detector and the same occupancy blocks as sensors as well. For that, I'm going to be using a sensor turnout creator tool here in the configuration. So I'm going to be saying that I create a sensor called B1, and I'm going to use the same event IDs as for the B1. And there's this make sensor button. So I can click the make sensor. And immediately I can see that sensor B1 active and sensor B1 inactive has shown up. Okay, I was not showing you the screen. I'm going to show you with B2. So I open the sensor turnout creation tool down here. I'm going to enter the username for the sensor, and then I'm going to copy paste the event IDs that I want the particular sensor to be listening to. And the same way as I have set up, as I have configured an output to be driven by the events created by the detector board, I can configure JMRI to listen to the same events and create a sensor like this. So now if I go to the sensor table, you can see that B1 and B2 show up in the sensor table. And if I move the train, you will not see that now. If I move the train, B2 goes active and then BM inactive. And eventually B2 will go inactive as well. So now the train is coming, enters B2, enters B1, exits B2. So the sensors in JMRI are following the same value as what we see on the layout and the layout panel. Unfortunately, I cannot show you both my screen and the layout at the same time. So you have to believe me here. I have created two sensors. Let's quickly create the rest of them. So I use username B3, copy paste the event IDs, make sensor, and then B4, copy paste the event IDs, make sensor, B5, copy paste the event IDs, make sensor, B6, copy paste the event IDs, make sensor. In some cases, a make sensor button actually appears directly on the configuration. In this particular case, I could use this make sensor button to create the sensor. The only problem is that I have inverted the meaning of the activation and inactivation. So if I create make this sensor from here, I would get an inverse sensor. That's not what I want. Let's quickly create a panel in JMRI. I'm going to create a new panel in Layout Editor. I'm going to show the grid. And we have plenty of space. I have a left-hand turnout in the middle. I have a couple of anchor points. And I have end bumpers on the far end. And now I'm going to add some track segments. I'm going to say B1, sensor B1. Let's see if this works. I'm going to say B2, sensor B2 at here. I'm going to say B3, sensor B3 at here. Let's see if this actually worked. Almost. Sensors were not associated with the block. I'm going to add B4. Set sensor B4. I'm going to add B5 here. Set sensor B5. I'm gonna add B6 to the top right. Sensor B6. Let's see how this worked. Still have some missing sensors, so I'm just going to double check everything. B2 has the sensor. B3 does not have the sensor, so let me add it. B4. Oops, mistake. B4 has the sensor now. B6 as well. Let's move around with the locomotive. Excellent. The JMRI sensors also follow the locomotive. Let's go the other direction. And now you can see that our JMRI panel is basically responding to the same events that are sent on the bus. All right, we are done with the sensors. The panel works and JMRI also works. Let's just save everything that we have here. This is the clinic test one. Sensors done. Sensors done. I'm going to show you another save feature because we are adding a lot of configuration that are actually written into the particular hardware pieces. And there is a way to make that configuration, like basically download the configuration and save it to a file on your computer. And this backup and restore buttons here are for exactly that purpose. So if you press the backup button, it will allow you to save the configuration into a file on your computer. And then later on, if you want to go back to a configuration that you've saved, you can use the restore button to load the configuration. So I'm going to save this. Excellent. So we are done with the sensors. We're not going to need the detector board anymore, at least not for the moment. So let's move on. Let's see if there is any questions. So there was one question is that saying that the LEDs were on until they detected their first event. Is there a way around this? The block detector isn't initially in an unknown state, is it? The answer is yes, the LEDs were on, but the LEDs were also not configured at all. So they were on because it was the default configuration. And in the default configuration, the line is inactive or low. And because it was an active low wiring of the LED, that's why it was lighting. Normally, it is up to the manufacturer of what the power on initial configuration is. I can tell you that the current production board that you can buy, which is the Tower LCC, it's these ones. They actually have non-volatile memory. And whatever the situation was at the time when you turned off the layout, it will save that value into its non-volatile memory. So when you turn on the layout next time, it's going to be showing the same value that it had at the time when it lost power. So I can unplug the wire and plug it back in, and it comes back and continues on exactly in the same place where it left off. Of course, if this is not desirable to you, then you have to create some sort of initialization script. And how to do that initialization script is probably a more advanced topic that goes beyond what we can cover here in this clinic. But there are many different ways. For example, some people do long logics in JMRI that send out events. If you have Tower LCC nodes only, it will also be possible to create one specific event saying, bring the layout back into its reset state. And then you can configure for every single Tower LCC input and output what that particular event should do for that particular output. So while the Railstars board does not have the ability to remember this upon power outages or layout turn on and off, the currently available RR circuit boards are significantly more powerful from this perspective. More questions? Yes, start of day. Yes, that's basically the same thing. There's basically a conversation about how the state is saved and restored in a distributed way on the bus. Yeah, the question was the JMRI version. I am using 4.7.3, I believe. Yes. Okay. So let's move on. We have our block detectors working. Let's get some turnouts working. So the first thing that I'm going to do is I'm going to actually plug in the turnout driver. Unfortunately, as I mentioned, I have not received the coil drivers from RR circuits, so I'm basically just using something that I botched up myself with a couple of strong drive transistors. And I have a separate power supply for the coils because, yeah, generally you don't want to run your coils from the same power supply as everything else. It can have some nasty electrical spikes. So I'm going to go back to the configuration. And we're going to the tower. The tower is the board that has the most complicated configuration available. And it suits very well a large number of different needs. So in this particular case, I have the turnout plugged into channel, oh, I forgot. I think it's 5 and 7 or 6 and 8. I'm gonna have to go and cheat here. I have to go back to my notes and say that channel 6 was the turnout closed and channel 8 was turnout thrown. Now, this is a double coil turnout driver. That means that I'm using two outputs to drive. One of them is going to energize the coil to set the turnout into close. The other is going to energize the coil to set the turnout into thrown. Both of them have to create just a short pulse in order to energize the coil briefly, and then they have to turn off again. Otherwise, I'm going to burn my coil. So what I'm going to do is I'm going to set, yes, input function disabled, that's correct. And the output function is going to be a pulse. And this is an active high coil driver. And for the pulse, I'm going to specify the delay, or the length of the pulse that I'm going to try to make as 700 milliseconds, 0.7 seconds. That's usually enough in order to throw a turnout. And this is turnout T1. And when this event comes, I want to set the line as active. So this is going to be the event ID for turnout thrown. Sorry, this is T1 closed. It's going to be the closed event ID. And then for T1 thrown, I set the input to disable, the output to pulse, active high, the interval to 700 milliseconds. And when this event occurs, I want to set the line to active. And this will be the thrown value. And there is no producer commands at all. As you can see, the configuration of the other circuits tower LCC is significantly more complicated. There are significantly more options and different ways of how you can use this particular node. You can compare the complexity that you see here with the complexity that you have the Railstars I/O board. The Railstars I/O board is significantly simpler, so it's somewhat easier to configure, but the abilities are fairly limited. So I could not use, for example, the Railstars I/O in order to drive a double coiled turnout driver, or somebody else would have to perform the pulse activation inactivation. So I'm going to save what's changed here. I'm going to make a turnout from what I entered there. And I'm going to go to the turnout table and see if it works. Excellent. You can hear the clicking of the switch machine, of the snap switch. I can also show you if the quality is high enough. I click the turnout button in JMRI, and you can see the switch mechanism flipping the points. So JMRI has the turnout now. That means I can also edit my layout panel. I'm going to set the turnout as T1. I say done. Now it is thrown. I click it. Now it is closed. I click it again. It is thrown again. Excellent. So the turnout can now be controlled from JMRI, and it is creating the appropriate pulses for my switch machine. Now let's go and see how we can make the panel buttons control the same turnout. The panel buttons are right here. These are two momentary push buttons that I'm going to set up so that it will send the same command that JMRI sends and receives in order to throw the turnout. So I go back to the tower. I look at my notes and I see that the turnout buttons are at output 11 and 12. So channel 11 is going to be T1 set closed, and channel 12 is T1 set thrown. No, that's wrong. Channel 10 is T1 set thrown. Oops. Channel 10 is the throw button. Channel 11 is the close button. Now let's configure them for the same event IDs. So these are going to have an input function. The button is wired up to be active low. There is no delay. And I am going to create a producer command when the input is on. I'm configuring the set thrown. When the input is on, I'm going to generate the event ID for throw. So when the input is on for the thrown button, the set thrown button, I'm going to generate the turnout T1 thrown event. That sounds good. And the set closed, I'm going to also specify it as an input that's active low. And in the producer, when the input is on, meaning active low, I'm going to set the turnout T1 to closed. I'm going to save the changes and see if this worked. Oh, I forgot to show you the screen output. So I was configuring the tower, and I've configured channel 10 for the turnout thrown and channel 11 for the turnout closed. And I have set the input function to be active low because my notes say that, that this button is wired up as a button to ground. And I have used the producer commands, the indications. When the input is on, I have taken the event ID for the turnout 1 closed, and I have pasted it here so that when this button gets pressed, it sends the event to the bus to close the turnout. And I did the same thing for the set thrown. I've configured the input function to be active low, and the input on action was the event ID that I got, that I have assigned to the turnout thrown button. And then I saved everything that's changed. And now we're going to go to the layout and test this. So I press the button, the turnout closes. I press the button, the turnout throws. This is awesome. Now I also have two indicator lights here whose purpose is to show the current value, current state of the turnout. So let's quickly set that up as well. The indicator lights are wired to the panel board. So I go to configuring the panel board, and I know that they are, I've already labeled them. So the turnout is closed. The turnout is closed, should be active when the turnout closed, and inactive when the turnout is thrown. The turnout is thrown should be active when the turnout is thrown, and inactive when the turnout is closed. I'm going to save the changes and go back to the panel. And voila. Now the indicator lights are always showing the turnout position. Now, because I have taught the same event to all the different boards on the layout, actually all the different nodes on the bus, both the JMRI computer, as well as the turnout mechanism and the panel, now it does not matter who is sending the particular command, everybody else will react. And I'm going to demonstrate you by going back to JMRI and pressing the turnout throw button there. So I'm going to pull up the panel. And I'm going to press right in the middle for the turnout. But I'm going to show you what the physical panel looks like. So if I press the turnout button in JMRI, you see that the turnout has thrown and the panel indicator has changed. I press the button again. The turnout has changed the direction again, and the indicator light has switched again. The same thing works in reverse. Now I'm going to show you the JMRI panel, and I'm going to go to the physical panel and start pressing the buttons. So right now the turnout is thrown. Now I'm in front of the hard panel. I press the closed button, and you see that the JMRI soft panel has switched the indication. And now I go and press the thrown button, and JMRI was updated as well. All right, so we have configured the panels for the turnout, and we have configured the buttons to throw the turnout and set the turnout to closed. And that means we can move on. Let's start and do some signaling. So we're going to do some really simple ABS style signaling. So don't have any more slides. I'm going to show you the layout. So I would like to make the signal heads work based on the indication and show the appropriate indication depending on what the particular block detectors are showing. First, I'm going to be doing something really simple. You can see there are many different, there are a bunch of different signals. Some of them are more complicated than others. So for example, S2 is a double-headed searchlight signal. That's going to be the most complicated to configure. But others are actually significantly simpler. So let's start with something easy. I propose that we start configuring the signal that I have shown here as S2R. That's this signal. It points actually towards the end of the layout. So it actually has a limited set of indications that it can show. Basically, if B1 block is occupied, I need this signal to show stop, which is going to be red in this particular case. If B1 is unoccupied, this needs to show clear or green. Now, this is a problem that we have already solved. It's actually the exact same problem as what we did for turning the light on and off, depending on what the block detector said. And you know, we can turn the light on and off. Here, for example, we use two events to create complementary indications. And I'm going to basically just configure this the same way. I'm going to configure the red and the green LEDs here to be complementary indicators of whether there is occupancy on B1 or not. So I'm going to go back to the configuration. I go to the panel node. It makes sense to always start by giving names to the particular outputs. So I'm just going to be quickly typing in the names. I'm basically looking at my notes, which is in the handouts that I have emailed you, and just copying the numbers. S2R green. Now I'm going on. Yes. There's just a few left. Excellent. So I've labeled all the tabs. So now I know where to go when I want to find something. What I have on the panels, these are the searchlight signals. This is a multicolor LED. It has a separate output for a separate input, actually, a separate lead for lighting a red LED and a separate lead for lighting a green LED. And I can basically simulate a searchlight signal by turning on the red only in order for to show a stop indication. I can turn on the green LED only in order to show a clear indication, or I can turn on both of them in order to show a yellow color. And this is actually fairly standard for searchlight signals that you can buy also for modeling purposes. I have decided to build everything on a panel so that you can see all the signal outputs at the same time. Because if I had put up wayside signals here, then you would be difficult. You would have like significant difficulty seeing what the particular indications are. So I want to set up S2R, and I want to make the S2R red to be on when block 1 is free, and I want it to be off when block 1 is occupied, or something reversed, right? I'm going to use this new feature. I can say, I can hit the search button and I can type in a text, and JMRI will give me some help in pasting event IDs. So I want red to go active if B1 is active, meaning occupied. Let's paste that. And I want the opposite. I want the red to go off when B1 is empty. And with the green, I'm going to do the reverse. When B1 is empty, I want green to go on. And when B1 is occupied, I want the green to go off. You can see I have a bunch of other uses for the same event ID. So I'm going to save. Let's see if it worked. It worked. So if B1 is off, the signal shows green. If B1 is on, the signal shows red. Green, red. And of course, the same thing if I drive the train out of block 1, the signal goes green. If I drive the train into block 1, the signal goes red. I'm going to show you again, because I forgot to switch to my computer. I'm going to show you again how this is done by configuring S3M, the mainline signal at the end of the line. So S3M red. So I want the red to go on when B4 is active. I want the red to go on. I use the search button. I press the search button, I type in B4, and when B4 goes inactive, I want the red to go off. And the green, when B4 is inactive, I want the green to go on. And reverse, when B4 is active, I want green to go off. I'm going to save everything that's changed. And now I'm going to drive. I'm going to drive over there. So when B1 is occupied, the light is red. When B1 is unoccupied, the light is green. Occupied, red, empty, green. Excellent. Let's do this one more time, because we have one more signal of the same type. Oops, that's not what I wanted. The S5M is another signal that needs to be done the same way. So S5M, red. Search for B6, active means on. B6 inactive means off. Green is going to be reversed. I need to save the changes. Throw the turnout. It's red when it's occupied. Oops, that didn't work. I mixed up something with the configuration of the green, because the green doesn't go on. Okay, let's take a look at that again. So this is S5M green. Yes, you can see that I have configured inactive on both sides, which is not what I meant. I wanted B6 active to turn off green. Let's try that. Switch back. See what's going on. Red, green. Excellent. That's exactly what I expected. Red, green. So I have done a couple of signals now, and these are two indication signals, which is not very exciting, but you can see how just the native event producer consumer model is able to solve certain simple signaling problems for your layout as it comes out of the box. Now, when we want to move on to a little bit more complicated signals, for example, those that have 3 indications, we're going to have to be using more advanced logic features. I'm going to show you the handout that I created for you quickly. This is the the notes that I was working off when I was setting up the particular names for the particular wires. And this is the rule set that we will be using for the signaling. So I have created S2R, S5M, and S3M, which are basically just two indication signals. They are relatively simple. Now, let's take a look and do a more complicated signal, which has like more than two indications. Let's start with S4R. S4R is a signal in the far right. This is the signal that we're talking about. The rules that we want for this signal is the following. If the next block, which is B3, is occupied, I want the signal to show stop. That means I want it to light red. If this one is unoccupied and the next signal is stop, I'm going to have to show yellow, which is approach. And if this is unoccupied and the next signal is not stop, but something else, then I want to show clear. So it's pretty clear. We can see already that we will be interested in the indication of the next signal, but we haven't configured the next signal yet. So we also need to understand when is it that the next signal will show a stop aspect or not. So this signal has to show stop if the turnout is thrown right now, or if the turnout is closed, but the next block is occupied. So there is an or statement there. So let's go into the configuration and see how the logic configuration looks like for the railroad circuits signals. So if B3, then red, as if B3 is showing red, then we show yellow, else we're going to show green. So I'm going to the Bakersfield panel. I don't care about the channels now. Now we go back. Now we go to the logic. Also don't need the sensor turnout anymore. The logic feature here has a built-in ability to create rules for signaling. And the rules for signaling work so that you have to use as many logic blocks as the number of aspects that you're trying to show. We're configuring S4R. So I have a stop, an approach, and a clear aspect. And then I'm going to configure what are the conditions for showing the particular aspect. And when those conditions trigger, then what is the action that I would like to take? And else, it is going to move on and try the next aspect. Because it is going through this if-else execution, it's important that you configure your aspects with the most restrictive aspect first. So I'm going to have to configure this as a part of the mast group because all of these form a single mast. So mast group, and then the last one is configured as last. And my help says that if B3 is occupied, then I want to show red. So I'm going to search for B3 active, B3 inactive. This is what sets the first variable. And because the Tower LCC has the ability to create logical ands and ors and nots of different variables, I'm actually just going to use the same variable twice because I don't need to use an and. So the condition now is if B3 is occupied, which is exactly what I want. Now I want to configure the action. I want to immediately do the following. I want to set S4R red to on and S4R green to off. So this will make sure, I forgot to say immediately red on and green off. This will mean that that the output of the LED will be red. Now, on the approach, I need to explain what this is, what B3 equals red is. So B3 equals red is T1 thrown or B2 occupied. So on the approach, if T1 is thrown, or B2 occupied. I always have to carry the event IDs in pairs because they represent one bit of information. So one turns the value on, the other turns the value off. And the action is going to be immediately set red to be on. And green to be on as well. So I set both red on and green on, which will create a yellow aspect indication. And clear, everything else is clear. So I set, I don't need any variables for this. As soon as the logic's execution has fallen through down here, then I can use this always true variable, and I will immediately set the green to on and the red to off. I'm going to save all the changes and see if this has worked. So we switch back to the node. So if the next one is occupied, it is red. That's excellent. If the second next is occupied, it is yellow. That's exactly what I expected. If there are 2 blocks free ahead, it's showing green. That's great. Now the turnout is also aligned. If I make the turnout to be misaligned, now S4R is showing approach. And that is because the train will have to stop short of the turnout that is thrown against you. If the turnout is closed, then S4R is showing green again. Excellent. This worked very well. Let's make a backup. We have configured enough many things that it's worth to make a backup. I'm going to back up the panel node. And I'm going to back up the logic node as well. There was a question whether the video will be available to pause and rewatch as needed. The answer is yes. In fact, you can actually pause it right now, and then you will be a little bit behind the real time as I'm doing it. Then you can basically catch up later and offline. If you have fallen behind because you paused the video, you can also play back at a higher speed, like 25% faster, if you can keep up with the speed that I'm talking and I'm doing things. And then eventually you will catch up to the live stream. But this is actually a good opportunity to take a quick break. So I'm going to back in, let's say, 5 minutes. Right now is 12 past. So I'm going to be resuming the clinic at 17 past the hour, whichever hour it is for you. If you have any questions, feel free to post it to the live chat window, and then when I'm back, I will be answering all your questions as well. there was one question, and the way I configured S4R was basically looking at the turnout and the block indication 2 steps ahead. And the suggestion was, why didn't I look at the turnout indication? Why didn't I look at the the signal indication just in front? The answer is yes. I can look at the signal indication. The problem is right now the signal just in front of S4R is dark. But if I configure it in a different order, the signals, then I can actually look at the signal indication just ahead. So let's do the other branch in different order. So I'm going to move on and configure S5R first, and then we're going to do S6R. And that way we can basically just perform a look ahead of the signal. So we go back to configuration, and we do S5R. I'm going to use again 3 indications, or 3 aspects, sorry, stop, approach, and clear. Here is my cheat sheet. S5R. It should be stopped if T1 is closed or B2. So it's going to be a masked group, T1 closed, or B2 active, inactive. Then immediately set red to on, and immediately set green to off. So this is the stop indication. Approach is much simpler because I only need to take a look at B1. We are still in a masked group. I say B1 active, B1 inactive, and since I only have one, I will copy paste it to the second variable. And the result should be immediately set red to on, and immediately set green to also on. This will show yellow in total. And then the final aspect is a last of the mast. I don't have any logic function. And I immediately set red to off, and green to on. You guys say I have a problem with my microphone, but now you also say that it's fine. 1, 2, 1, 2, 1, 2. According to the feedback that I see on here, it seems good at the moment. Okay. Okay, you guys are also saying that it's fine now. So I have edited a bunch on the signal node. Let me go and save all the changes. And let's go and see what it had done. So I'm going to go and flip the turnout. Check the occupancy events. Doesn't seem to be working at all. This is what I have configured. So I'm going to go back and see what I have mixed up. That was one mistake I found. So right now, when both the next two blocks are free and the turnout is lined in the right order, it is showing as green. If the turnout is lined against, it's showing as red. This is the signal that we're looking at. And if the turnout is lined, but the next block is occupied, it's red again. And if the next block is free, but the second next is occupied, it is showing yellow, which is approach. And that's exactly what we meant. That works great. And now we can move on. Now we can move on to doing S6R. And now in S6R, we can actually use the already configured and computed aspect. So I'm going to be configuring S6R stop approach and clear. It's going to be a masked group, and last. Now S6R, if B5 is occupied, then let's make it red. So if B5 is occupied, then we're going to make it red, and there is only one variable here, so I'm just going to copy paste the same variable down. Then immediately S6R red on, S6R green off. Now comes the else part. As if the S5 is showing red. So it can show three things. It's either red, which means both red is active and green is active. Sorry, if it shows red, then that means red is active, green is inactive. If it's showing yellow, then both of them are active. If it's showing green, then the green is active. So S5 red I can define as S5R green is inactive. And that's a pair of events, so I can actually listen to that. So I'm going to find S5R green, and I'm mixing up inactive and active in order to invert the definition of the variable. And since I only have one variable, I'm just going to copy paste that. And if it's approach, I want immediately, since it's the approach, I'm going to set both of them as active. And that should be fine. And finally, the clear, again, has no condition. I'm just going to be saying null means immediately red should be off. Green should be on. I forgot to check this. Okay. Yeah, let's save changed. And let's go test. Again, we already see a clear indication. That's pretty good. Now we see an approach indication. And now we see a stop indication. This works wonderfully. And now, of course, it is clear again. But if the turnout is thrown against, then you get an approach indication at block 6, and you're going to get a stop indication at block 5. Nice. So we're getting good with our signal coverage here. So basically the way, I think Ken was the one who suggested this in the comments, that actually works wonderful. We have a couple of more signals. I'm going to be talking less here. I'm just going to basically click through here so that we can move on and save some time. You can basically watch me clicking a lot in JMRI. So we've got a 6R, S3R. here I cheated a little bit because I know that the activation and inactivation events are always next to each other. I can basically just change the value, and I know that's going to be the inactivation event. Let's see if it worked. So I can already see a stop indication. I see an approach indication. I can see a red. And I can also see a green. Excellent. So S3R has worked. Now comes a little bit more interesting one. We have a double-headed signal. A double-headed signal, for us, it has 4 output lines. We have the top head, red and green, and we have the bottom head, red and green. So we need to control fundamentally 4 outputs. Incidentally, 4 is exactly how many different actions one particular logic evaluation can have by default. If you need more than 4 actions, you can use the function called ladder group. However, if we look a little bit more carefully at the logic that is needed for signaling the double-headed searchlight signal for route signaling, this is important. We are doing route signaling here. You can actually configure the 2 different heads to have separate signaling logic. Because the 2 heads, let's say the main head and the siding head, they have exactly the same type of logic that we've already configured, just independently applied. So let's do just that. Let's apply the same kind of logic that we've already configured here independently to the main and the main and the siding. So S2M stop, S2M approach, S2M clear. Let's configure this. If T1 is diverging or B3, then we show stop. Last, single. If T1 is strong, or B3 inactive, then immediately do 2 things. S2M red on, green off. Red on, green off. As if B4, and I need it twice because there is only 1 variable here. Then immediately red on, green on. And the third one is going to be null true, immediately red off. Oops, I mistyped it. green on it immediately as well. Save this. So I can see clear on the top head, stop, and I can see approach. And if the turnout is thrown, I will always see stop indication, dependently of what's the next. That's clear. And let's do the second head as well. Stop. Approach. Clear. Must. Single. The slave is this one. So if T1 equals closed, oops, T1 closed, or B5. Then immediately red on, green off. Approach as if B6. B6 on off. I only have one variable, so I just copy paste the same for the second. On off. Then red on, immediately green on, else last, no logic function, immediately red off, green on. Save all. Let's go test. I've got clear, I've got red if the turnout is thrown. I've got red if the next one is occupied. I've got yellow if two of them are, if the second one is free. That's brilliant. If I throw the turnout, I got clear over, clear over stop. And if it is thrown, then I've got stop over approach. And if the next block is occupied, then it's all red. So now you have to stop. There is one signal left. Let's just quickly do that as well. I'm also going to create a backup. So in order to back up, I'm just going to use the backup button here. I've only been configuring the tower, so I'm just going to back up the tower. Let me see if there is any question. So Dick was basically explaining in the comments how the masked conditionals are working. Basically, what we have is for the ABS logic, we have 3 lines that we need to evaluate. If the next block is occupied, or let's say a turnout is thrown against me, then I need to show a stop aspect. If this was not true, then I look further ahead. If the second next block is occupied, I'm going to show an approach aspect. And if neither of these two has caught me, then I'm going to show a clear aspect. And this is exactly what the Tower LCC masked conditionals are doing. So this is not the Tower LCC, this is the Tower LCC. So the stop is the first entry in the masked group. And I'm configuring it so that it sets the logic for this line. If that logic conditional is not true, it will fall through to evaluate the next logic conditional. And that I configure to do this logic line. And then if that has not caught the evaluation either, then it gets to the last logic line where I have no condition at all. I say null equals true. So this will always stop the processing, and it will always execute if the logic conditional processing has gotten this far. So there is only one more signal left. That is S1M. And I'm going to take maybe 2.5 minutes to configure this so that we have a full house of signals. If B2, then and now the second condition basically requires me to figure out if the double-headed signal is all red or not. And I'm going to basically do this by looking at the green outputs from each of the signals. So S2M green inactive. I flipped the two conditionals, so to test inactivity. And I need to look at the S2S green inactive. S2S green inactive. If both of them are true, meaning both of them are red, then I'm going to show an approach. Red active. green active. And then finally, I do the usual null equals red off. Green on. Save everything. I switch to the layout. I've got red. Oh, this doesn't work very well yet. It looks like I mixed up something. So if it's red over red, it's yellow. If that one's approach, this one's clear, that's fine. If that one's clear, this one's clear. If it's red over red, we're good. If it's red over red, it's yellow. If it's red over yellow, it's clear. Excellent, this works as well. So that means we have all of the signals correctly showing the ABS signaling aspects. If there is any question about signaling now would be a good time to ask, because otherwise we're going to move on. There is one more item left on our agenda, which is the railroad crossing. And then once we have the railroad crossing, we will conclude the clinic. So let's see how the railroad crossing works. So with the railroad crossing, we have basically two problems that we need to solve. One of the problems that we need to solve is we need to make it blinking. In fact, we need to make it blinking. Both lights have to blink, and they have to blink alternating each other. Fortunately, the Railroad Circuits Tower LCC actually has features to do that. So let's take a look at where I have wired it up. So I have wired up the crossings to 13 and 15. I go to the configuration. So 13 is crossing 1, and 15 is going to be crossing 2. These are both active low outputs. So I've set the output function to blink active low. And there are two blink functions, which is great for us because that's exactly what we want. So one I set to blink A, active low, and the other I set to blink B, active low. I'll have to set the interval for the blinking as well. I'm going to be using 600 milliseconds blinking. I think that is close enough for what we expect railroad crossings to do. And now, since this is an output, now I need to actually define the events that will turn it on and this will turn it off. So as an initial, I will basically say that when B2 is active, the line should go active. When B2 is inactive, the line should go inactive. And I need to do the same thing with the other channel as well. When B2 goes active, the line goes active. When B2 goes inactive, the line should go inactive. Now I'm going to save all of this. And let's see. I'll switch over to the layout. So you can see that now when the train is occupying the block on which the railroad crossing is set up, the crossing lights are blinking, and the crossing lights are blinking alternating each other. And hopefully, if the block goes clear, then the crossing lights go also out. And for the moment, this is not influenced by the turnout or anything. It's just the occupancy of the particular block. So this is one potential way of how you can do a crossing signal with the tower LCC and using its blinking functionality. There are more advanced ways of how you can do railroad crossings. In a later version of this clinic, I will have all the I/O boards from railroad circuits, and then I will have the ability to do the occupancy detection of the turnout separately. And when the turnout will have its occupancy detection separately, I will have the ability to do to turn on the crossing gates, start them blinking when a train is approaching. So for example, when B3 or B5 is going occupied. So roughly at this point, oops, sorry, I went too far. So at this point, the crossing gates should go on because there is an approaching train. But as soon as the train leaves the turnout, I'm halfway bridging the block. As soon as the train leaves the turnout and is already in the B2 section, but BT is free, the crossing gates would have to go out already. And it is possible to configure this with the appropriate use of events and the logic functionality of RR circuits tower LCC boards have the ability to detect the order in which occupancy detectors are triggered. And based on that, you have the ability to deduce the direction in which the train is traveling. And then you can turn on the crossing gates with an approaching train from farther away and turn them immediately off when the last detected component of the train has passed the crossing gates. There's only one feature left from the list of desired features, and that is right here. I have this mainline lockout on the panel. The intended functionality of the mainline lockout is that the dispatcher can set a flag, and if the dispatcher takes control of the mainline turnouts should be locked out, meaning the local push buttons should not have an effect on the mainline turnouts. And this is possible to be done with the Tower LCC boards. The Tower LCC boards, and today the input buttons are wired to Tower LCC. The Tower LCC boards have a feature called gating. Their input buttons can be gated. I can configure a pair of events that will gate the input buttons from working. And if those events say the input should be gated, then even if the customer presses the input button, the event will not be generated and not be sent to the bus. So let's create the mainline lockout. The first thing is I want to have the LED that is on the top left corner of the hard panel to work. And I know I have set this to channel 9. So this is the mainline locked. It's an output that is active low. I'm going to have a pair of events that set it to on and off. And locked will be on. And unlocked will be off. I create this sensor in JMRI. And I save this configuration to the Tower LCC. Now I go to my JMRI panel, and I'm going to add a sensor icon for mainline locked. I add the label to it as well. I forgot to show you what I'm doing. So I added a sensor, and this mainline locked sensor, I can click in JMRI. And if I click it in JMRI, I'm going to show it. It's going to be shown on the panel. Of course, right now this doesn't do anything. It's just basically I'm clicking the button on the JMRI panel, and then it lights on the hard panel. It doesn't have any effect. The way I configured this is that I took channel 9. I configured channel 9 to be steady active low. I gave the name mainline locked, and I configured 2 consumer commands to set the state of the line state to on and off, respectively. And then I took the events, and I said the off will be the inactive event, the on will be the active event. I gave mainline locked as the username, and I clicked the make sensor button here. And that caused JMRI to put a new entry into the sensors, in addition to all the block occupancy detectors that we had. We now have the mainline lock sensor here. And if I click it, it will keep changing the light on the panel. So this is basically a light on the panel. It is doing nothing. So I can still go and flip the turnouts left and right. So now next what I'm going to do is I'm going to wire up so that if the mainline lockout is active, then these input buttons will be gated. So I go back to the configuration. I find the input buttons, the T1 set closed and set thrown. And I'm going to go to the consumer commands. And I will use the gated function. And the main line is locked. I want this to be gated. And the main line is unlocked. I want gated to be off. I'm going to save the changes here. I could use event 1 and 2 for consumers, and I don't have to use event 3 and 4, but I'll just go there. And I'm going to do the set thrown as well. Gated on, gated off, and gated should be when the sensor is active. Gated off should be when the sensor is inactive. Inline locked inactive. I'm going to save changes. Select the sensor a couple of times. And now comes the interesting moment of truth. That clearly didn't work. Let's try the veto. Maybe I mixed up gated and veto. Veto on, veto off. Veto on, veto off. I save the changes. And I'm locked. This clearly didn't work either. All right. We're going to ask Dick about this. What did I configure wrong? See if he has some smartness to contribute to us. Okay, Dick has helped us kindly in the comments. Excellent. So this work now works as expected. So right now the mainline lockout is inactive. So I can use the buttons to throw the turnout. But if I go and turn on the mainline lockout, I turn on the mainline lockout, then the buttons will not do anything anymore. So the operator can go to the panel and press the button there, but because the dispatcher has taken control of the mainline turnouts, those buttons will not work at all. And the difference that was necessary in the configuration to make this work was that I had to set the line that was doing the producer. This is the input line that is connected to the button that I was pressing. And on this input line, I had to set the produced event from just input on to gated on. And when I set the producer to gated on, I could configure consumers for the mainline lockout event. And the mainline lockout event has basically then gated the functionality for the push button. All right, so this basically means that we are finished with our layout. It is fully functional now. All the signals operate. The turnout works, and the turnout indication works. And that was basically what we tried to achieve today. So if you have any more questions now, please ask them in the comments. Otherwise, I will thank you for your attention and conclude the clinic. All right, there was a question of what is the target duration for the clinic? This clinic is scheduled for a night session, which starts at 8:30, and it can run until people keel over. So the desired duration is 2 hours. Right now we are actually at 3 hours. There was a question about the turnout detector. Yes, I only have 6 detector channels, so I could not set a separate detector for the turnout. We are not desiring to trim this down into 45 minutes. This is scheduled to be running for 2 hours. All right, then thank you very much. I will go offline now, and you can send me any questions or comments in email through to the OpenLCB group. I will show you the contact information. Here are some useful links and how to contact us in the Yahoo groups for OpenLCB or the Yahoo groups for layout command control. I am a member of both of those groups, so I will be receiving your email. Thank you very much for your attention. And I hope to hear from you in email about feedback about this clinic.